Hello and welcome back, everyone. Formal charge. Let's go ahead and let's just jump in and let's get this figured out. Obviously, if we're talking about charge, we want to know if something is positive or negative, right? And formal just it means that what we're doing is sort of officially trying to find out, officially, is the charge correct? Does this make sense? And all this is in terms of Lewis structures. So if you're watching this video, I have to assume that you've watched previous lessons on writing Lewis structures for our molecular compounds. And then we've looked at polarity and electron density and things of that nature. This is a lesson that takes all of those concepts, and then we take a look a little more in depth, sort of quantitatively, how correct are those structures, and is there, can we use this tool as formal charge to figure out a better structure if possible. And where this really comes into play is where we have complex structures where there's not one central atom, and like with resonance structures. So with that, let's just jump in and let's go ahead and take a look. So let me go ahead and let's clear this board here, right? Let me get that back the way it was. So the first example that I usually talk about with everyone is hydronium. All right, so hydronium, it's an ion. All right, so the hydronium ion. So this is really easy. So formal charge, we tend to write it out. Formal charge equals the group number of the atom, all right, minus the number of electrons in lone pairs minus 1/2. All right. Let me back that up. Sorry about that. Minus 1/2 of the electrons that are in bonding pairs. Okay. So this minus 1/2 of that. Okay. So let's just, to do this, we have to have our Lewis structure. Well, we know from our Lewis structure from this that the first step we would do would be to count up all the atoms. Well, we need 6 for oxygen. Each hydrogen brings in 1, so there's a total of 3. So if you look at that, that looks like 9 electrons. However, this charge here means that an electron was added somewhere else. So technically it's lost an electron. So we have to subtract an electron, right? So we need a total of 8 electrons total for this structure. So rule 2 says take your atom that you know is going to be the central atom, bond everything else to it, and then add lone pairs until you satisfy the octet rule and you have the correct number of electrons. And so here we can see that hydrogen is not going to have any lone pairs, so we would just put the lone pair on the oxygen, and that makes sense because now around the oxygen there's 2, 4, 6, and then 8. The octet rule is satisfied, and we can see around each hydrogen the duet rule is satisfied just with electrons in that pair, electrons in that pair, and electrons in that pair. All right, this is an ion, so we always complete that by putting our charge symbol. In this case, it is positive, not negative. Now, all we do is, now we calculate formal charge. So off to the side, we're going to go formal charge, and then I usually start with a central atom and work my way outwards, and you'll notice in a lot of examples you might find in textbooks, other tutorials, that tends to be the case as well. It's just a standard practice. So the formal charge on the oxygen, we'll write that as a subscript, equals the group number of the atom. Well, we know that oxygen is in group 6, all right? And if you don't can't remember that, go to the periodic table, and we see over here where oxygen is, right? And where oxygen is right here, you can see that we would have to count over 1, 2, 3, 4, 5, 6, right? And that gets us to oxygen, all right? So it's group number 6 minus the number of electrons in lone pairs. On the oxygen, you can see there's just that one lone pair right there. And so we would say 6 minus 2, right? Minus 1/2 the number of electrons that are in bonds. Well, around the oxygen, we can see that there's 2, 4, 6 electrons that are in bonds, correct? So we would come over here and put a 6. All right, so 6 minus 2 is 4. 4 minus 3, which is 1/2 of 6, is our positive 1. And sometimes you'll see these things written where they'll write 1 plus or plus 1, just to denote that. You can do that if you're so inclined. All right. So now the formal charge of hydrogen. Hydrogen is in group 1. Number of electrons in lone pairs. That should never be the case for what we're going to be looking at whatsoever. So that is 0 minus 1/2 of the number of electrons in bonds. Well, each hydrogen has one bond. That's 2 electrons. So 1 plus 0 is 0 minus 1, which is half of 2, is 0. And so what we are seeing here is that each hydrogen is basically a neutrally charged atom in this particular structure, and that the oxygen is carrying a positive 1 charge. And so the positive 1 charge that we see here comes from this oxygen right here carrying a partially positive charge due to the bonding nature of this structure. Okay, so this formal charge here verifies what we've already seen, what we've memorized, what we've looked at in tables when we write hydronium as H3O+. Formal charge, this math right here, is verifying that for us. Okay. So now let's move on to some other example. Let's see, the next one, let's do carbon monoxide, all right? Let's do carbon monoxide. So we can see here, carbon, there's one of these, oxygen, there's one of these, there's 4 valence electrons here, so that's 4, right? The oxygen, we know, brings 6 valence electrons, so we know we need 10 valence electrons total, right? We need 10 valence electrons total in this particular structure, all right? So now, let's build this thing. Rule 2 says we need to bond everything together. So we've got carbon bonded to oxygen. Rule 3 says add lone pairs until you satisfy the octet rule. So if we look at this, we can see that we've got 2, 4, 6, 8, 10, 12, 14. That's much greater than the 10 that we said we needed. We know, remember we said we need 10 electrons total, right? Well, that looks pretty horrible. Let me try that again. We know we need 10 total electrons. So we know that this single bonded structure, that's not going to work. The octet rule is satisfied for each, but we got too many electrons. And as we've learned from previous lessons, too many electrons, we're going to have to increase bonds. So we just counted 14. That's 4 extra. We can kind of see that there's a good possibility here that what we need to do is probably add 2 more bonds that would account for those 4 electrons. Now, if we look at this, we've got 2, 4, 6, 8, 10. So there's a total amount of electrons. That's good. If we look at the octet rule, 2, 4, 6, 8. Very good. 2, 4, 6, 8. Very good. All right. So far, so good. Now let's take a look at formal charge and see if we can verify this. So formal charge on the carbon equals group number, 4, minus the number of electrons in lone pairs, that'll be 2, minus 1/2 the number of electrons in bonds. Again, we see 3 bonds, so that would be 6, right? So 4 minus 2 is 2, minus 3, right? That gives us a -1. So now we come over here, we've got formal charge on our oxygen, so group number 6, minus the number of electrons in lone pairs. This oxygen right here, it has 2 in lone pairs, minus 1/2 of the number of electrons in bonds. Again, that is 6. So 6 minus 2 is 4, minus 3 is our +1. And so we can see that the sum equals a 1 plus a -1, right? Which equals 0. All right. So this makes sense because when we write carbon monoxide, we don't see a charge symbol here. That makes sense. That the sum of the charges equals 0. That makes sense. What we do see here is carbon monoxide, that the carbon is carrying a negative charge and that the oxygen is carrying a positive charge. So we come back over here and we write those charge symbols accordingly. So what that means is if we looked at electronegativity, right? So we see that, if we go to our electronegativity scale, which we've talked about, oxygen, we can see over there is 3.5, carbon 2.5. And so from what we've studied, we know that there would be some polar interactions going on here back and forth. And carbon monoxide, it has a few behaviors that occurs with it. But this formal charge here sort of lets us know that, okay, this is probably the best structure that we can get for this. All right, let's move on. Let's move on to one more example. Let's take a look at something a little more complex. All right, let me clear our board here once again. Let me get rid of all this. This time, let's take a look at something a little more, I don't want to say challenging, just let's go with something a little more complex, et cetera, a little more time consuming, et cetera, et cetera, et cetera. So let's go with dinitrogen trioxide. All right. You can see here, this is a molecule where there probably is not going to be one central atom. All right. There's not going to be one central atom here. And what I want to bring to your attention is the atom that has the lower electronegativity value will tend to be centralized in the structure itself. And we can see here nitrogen has less of a electronegativity value than oxygen does. So with that said, when we go to bond this, it makes sense that our central atom, we're going to build everything around that right there, knowing that the nitrogen has the lower value, right? And so I'm just very quickly going to do our work. We know nitrogen right here, that has 5 valence electrons, right? So 5 times 2, so there's our 10 electrons. And then, oxygen, it brings in 6 valence electrons. There's 3 of them, right? So that's 18, so we're going to need 28 electrons altogether. So we're going to need 28 electrons total. All right, so let me go ahead and clear this board. 28 electrons total. All right, so now rule 3 says bond this thing together. So we've got 2 oxygens. Kind of makes sense that there's going to be an oxygen here and an oxygen here. I mean, we could make an argument that what we do is we put one in here, and then those are 3 of them. There's an argument for that. If we could get this to work out with 20 electrons, what we would do is ask ourselves, what does the formal charge show us works. And so I'm going to challenge you to do that, to come back to this structure, and we can take a look at that to see, is this a favorable form or not? But our first instinct is to probably take a look at some sort of symmetry, which gives us this. And things occur in nature according to what is going to take the least amount of energy to accomplish. That's just the way thermodynamics it works, right? So we've got something like this. So now it makes sense on one of these nitrogens to go ahead and put an oxygen atom. So I'm going to come down here and I'm just going to put an oxygen atom right there. Okay. So let me move this over because I know I'm going to need some extra room for my math work. I'm just going to kind of put that right there. So now let's take a look. We fill the octet rule. If we do that, we go, so around this oxygen, 2, 4, 6, and then 8 for that bond that's there, with this bond that's right here on this one. So that's 2, 4, 6, 8. Around the nitrogen facing our left, 2, 4, 6, 8. And then in the middle, 2, 4, 6, 8. And then the oxygen on the right, 2, 4, 6, 8. This gives us 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. That's 32. Well, that's 4 more electrons than what we need. So we think, wait a minute, 4 more electrons, 2 bonds. So probably somewhere I'm going to need to add 2 bonds. So we back up, and then we ask ourselves, all right, let's go back to rule 2, where everything is just bonded together, and ask ourselves, what could we do here that could, I don't know, get this working? Well, we need 2 bonds, so we're going to be double bonding something. So my first instinct is to go back and think about what I know about oxygen, right, and what I know about nitrogen. Individually, we know that nitrogen wants to form up to 3 bonds, and oxygen wants to form up to 2 bonds. And we've seen in many structures where we have oxygen double bonding quite frequently. So my first instinct is to look at oxygen as that's where we're probably going to have, where the double bonds are going to occur, not between the 2 nitrogen atoms. Okay, that's my first instinct, is to think that way. So another way is to think of this. You see how right here, nitrogen 3.0, oxygen 3.5. Oxygen has a greater electronegativity of 3.5, so it, for lack of better words, it has a greater pulling force. It has a great ability to attract things to it because it has that higher electronegativity value. So that's another piece of data, another piece of information we can use along with these Lewis structures here to help us determine that what we may want to do is go ahead and double bond some oxygen. So which oxygens? Well, I don't know. Definitely this one. Now the question is, do we double bond this one here or this one here? Well, if you look at it, they're both single bonded to the same nitrogen. So if you remember our discussion on resonance, that it's probably not going to matter which one you bond it to, because either way, you've got a double bond and a single bond to the same nitrogen, to the same type of atom, oxygen. And so either way, it's going to work itself out. So I'm going to just go ahead and put that right there, just because, I don't know, I felt like doing it. For now, anyway, that's the reason why. All right. So hopefully you're following that. If you're not, I advise you to go back and rewatch those lessons before on how we get that. There's a lot of sort of knowledge, pre-knowledge that I'm hoping you've brought with you to this particular lesson. Now we've got to do our formal charge. What you need to keep in mind, though, is this. There are 3 different oxygens, and those oxygens, since there's 3 different oxygens, we need to, after we finish adding these lone pairs, we're going to need to calculate our formal charge. We're going to need to look at each individual oxygen separately to try to figure out what in the world is going on with the formal charge. So right now, if we look at this, we've got 2, 4, 6, 8, 10, 12. All right. Let's see what happens if we finish adding in our lone pairs. This oxygen on our left needs 3 lone pairs. This nitrogen right here, it's already good with 2, 4, 6, 8. It is good to go. This nitrogen right here, 2, 4, 6, it is not good to go. So that makes sense that we would probably need to do that. Now, once again, that falls in the line with this concept here that nitrogen wants to form 3 bonds and it has a lone pair already. It falls in line with what we know already about nitrogen, right? This oxygen down below, it has 2 bonds. That's 2, 4, 6, 8. And this oxygen on the right, 2, 4, 6, 8. All right? So now we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. We are good to go. This structure seems to be working for us. Okay? So a long-winded way of explaining that, but I wanted to give you a step-by-step to kind of really help you figure out and really analyze why each step of the way I'm kind of doing what I'm doing. What was my rationale? What is my rationale in this? Okay, keep that in mind. Very important. Now we just do all of our formal charge work. So we could call this right here, say, we can call this one oxygen 1. I'll call this oxygen 2. I'll call this oxygen 3. All right, sorry about that. And so, I can call this nitrogen 1. We can call this nitrogen 2. All right, when it comes time for that, we can do that. So right now, let's go ahead and do our formal charge work. So we've got the formal charge for oxygen 1. All right. Group 1. Group number of the atom, oxygen, 6. Right? And then oxygen 1, number of electrons in lone pairs, that's 2, 4, 6. Minus 1/2 the number of electrons that are in bonds, that's 2. So what we get right here is a -1. 6 minus 6 is 0, minus 1 is a -1. And so that lets us know that right here, we can come over here, put that negative charge, and see how this works out. So I'm now going to erase and put and get rid of that right there. Well, I guess I can leave that there for now. I'll leave that there for now. Okay. Let's come back here. Let's do the formal charge on oxygen 2. And that's not O2, that's a subscript for a subscript. The 2 is a subscript for the subscript O for the subscript formal charge. All right, so group number 6 on number 2. All right, excuse me, oxygen 2. So now what we've got is we've got the number of electrons in lone pairs. So that's 2, that's 4, right? And then we've got 1/2 of the electrons that are in the bonds. So that's 2, that's 4. So we've got 6 minus 4 is 2, minus 2 is 0. So on oxygen 2, we're going to call that a 0. We're going to call that 0. All right. We're going to say that that's neutrally charged. All right. The third oxygen, group number 6. And it's bonded the same way. There's number of electrons in lone pairs. Well, that's 4, right? minus 1/2 of the electrons that are in bonds. That's 2, that's 4. So once again, 0. So those two oxygens are carrying a neutral charge. Okay, those are carrying a neutral charge. So now we come over here and we want to do the formal charge on nitrogen. The nitrogens are bonded differently. So once again, I'm going to come over here. I'm going to call this nitrogen 1. I'll call that nitrogen 2. So the formal charge on nitrogen number 1. Group number is 5. So remember periodic table. So, right, we've got 2, 3, 4, 5. Group 5, right? Group 5. So that's 5 minus the number of electrons in lone pairs. We see absolutely none on that one. So minus 1/2 the number of electrons that are in bonds. That's 2, 4, 6, 8, right? So half of 8 is 4. So the 5 minus 4 is the positive 1. And so we see here on this nitrogen here that is a positive charge. And so far, this is looking pretty good. A positive 1 and a negative 1, right? This negative 1 and this positive 1 equals 0. And we see no charge there. So far, so good. So what we can do is we can already be thinking that this last nitrogen, if we do everything correctly, we should probably get no charge on it, right? It kind of would make sense. So the second nitrogen, group 5, minus the number of electrons in lone pairs. Well, that's 2, right? Minus 1/2 the electrons that are in bonding pairs. That's 2, 4, 6, right? So 5 minus 2 is 3, minus 3 is 0. Hey, that worked out perfectly. That's exactly what looking at our structure, we looked at that and said that makes sense, that should happen. And so the sum of the formal charges, you literally just count each one of those and add them up. So that's -1 plus 0 plus 0 plus 1 plus 0 equals 0. Check. And so this is looking like what we would call a favorable structure. This is a favorable structure. The formal charges should be as close to 0. As many atoms as possible should be as close to 0 as possible. And here, almost every atom is 0, with the exception of 2 of them. And you can see that what's going to probably happen is that there's going to be some resonance back and forth between the double bond and single bond on that nitrogen right there, right? There's probably going to happen. And you can see that the only thing that would happen would be that the negative charge here would shift to here. That's really all that would happen with that right there. And mathematically, we know that makes sense. Structurally, we know that probably makes some sense as well. Okay? All right. So to wrap this up, what I want to do is show you another way of some struggles that I know I've seen in the past, where you can build a structure, people can build a structure, and then it follows the octet rule. It follows rule 1, 2, and 3, and it's built very, very well. It's built properly. You know, the octet rule is satisfied for everything, etc. But in the end, what happens is if you were to look at the structure itself, it doesn't work itself out as well as it could be. So what I'm going to do is move this to the side, because we know that this is a good structure. We know that this is a good structure. Let me remove that. That's a good structure right there. So what happens if by chance we have, let's just say, earlier, when we first started this particular discussion, the question was, hey, where do I start putting double bonds? And so one of the things I noticed is that students tend to want to put maybe a double bond right here and want to know, well, why doesn't that work? Well, let's go ahead and do that. Let's go ahead and come back here, back to our original setup, and then we go, oh, well, we know there's an oxygen, and so someone says, oh, double bond that because I've done some structures in the past where I saw nitrogen double bonded, so they do that, and then they just put a double bond on another oxygen, and then they felt the octet rule, and they realized that, wait a minute, if I fill the rest of these in, what happens here? So, this right here has 2, 4, 6, 8, and then this one right here also has 2, 4, 6, 8, just in bonds, right? Okay. And so we look at this, and we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Oh, I forgot to put, my bad. I forgot to put that lone pair right there. So then 28. So this structure right here would work, right? So I'm going to back this up, and then what I'm going to do, let's clean this up for you. So if earlier in this you were watching that and you were like, hey, he wrote that wrong, I have fixed it, but good job if you caught that, all right? So we know this works for rule 1, 2, and 3 as far as structuring it and getting the total number of electrons that we need, which is 28. So now what we would do is we would look at this molecule and ask ourselves, hey, let's do all this formal charge work, all right? So formal charge on, let's go with oxygen 1, and we're going to, what we'll do is we'll assign this number 1, we'll assign this 2, we'll assign that 3. Formal charge on oxygen 1, group number 6, minus the number of electrons in lone pairs, that is 6, minus 1/2 of the number of electrons in bonds, that is 2. So 6 minus 6 is 0, minus 1, -1. So we know right here we have a negative. No surprise, it's the same as it was over there. Okay. So now let's go the formal charge on oxygen 2. All right. That is group number 6 still. Number of electrons in lone pairs. Now you can look at this and you see, wait a minute, it's bonded the same way as number 1. So technically we know that the math should work itself out exactly the same. So I can come over here and I can put a negative symbol here. All right. Now going no further, we look at this and we say, wait a minute. So far doing this, we have an overall net charge of -2, but notice there's no charge on this particular molecule. So without going any further, with 3 atoms remaining to calculate the formal charge for, it makes sense that 2 of them should come out to a positive value so that it can equal out to 0. So let's see what happens here. Let's go with the other oxygen. Formal charge on oxygen 3, again, group number 6. All right. The number of electrons in lone pairs, so that is 4 minus 1/2 of the electrons in bonds, that is 4. 6 minus 4 is 2, minus 2 is 0, right? So to put a charge symbol on that 0. So if our math is correct, we might be able to see that the nitrogens end up having a positive charge. So it doesn't matter. I'm going to call this nitrogen 1, nitrogen 2, just like I did before, so we can better compare or make it easier to compare. So nitrogen 1. So nitrogen 1, group 5, minus the number of electrons in lone pairs, that is 0, minus 1/2 the electrons in bonds, that is 8. So 5 minus 4 is 1. So we come over here and we realize, all right, there's a positive charge there. If you look carefully, this nitrogen and this nitrogen are bonded exactly the same. They have 4 bonds, and they have no lone pairs. So that means that the formal charge on nitrogen 2 has to be the same as 5 minus 0 minus 1/2 times 8, which is 1. And so we know that we get a positive symbol here. So looking at this, the sum of the formal charge is -1 plus -1 plus 0 plus 1 plus 1. And, that's a -2, that's a +2, 0, right? Okay, so the numbers work themselves out. Overall charge is 0. So the question is that good? Will that work? The answer is no. And the reason why is this. It goes back to energy and what is going to occur that requires the least amount of energy. If this oxygen atom and this oxygen atom are both negative, that's putting a greater pull on the overall structure than just one oxygen having an overall net charge where the electron density for that oxygen is slightly greater. Then both of these nitrogens are being pulled towards the 2 single bonded oxygens. That requires more energy than it does for just one of the nitrogens on this molecule to basically have some of its electron density shifted in just one direction versus 2 directions. All right? So it's all about energy and how it's going to stabilize. So what we would say is that this is not a favorable species. And that's actually how you say it, not a favorable species. All right? So species refers to just this particular structure, this particular molecule, this particular form of the molecule. So like in biology class, if you talk about a species, you talk about the specific form of something that's related to something else, right? So remember that whole genus species thing? So species is more particular, more specific, right? And that's all that means in chemistry as well. It just means the particular molecule that we're looking at, this species here. So this is the least favorable species of the 2. So this would be what would occur. We would say that this is a favorable structure for this particular molecule. But wait, there's more. I know. You're thinking, oh my gosh, what more could there be? Well, all we're going to do now is real quick apply what we know about our VSEPR theory, right? So remember VSEPR, all right, valence shell electron pair repulsion theory. What we want to do is apply what we know to this. Okay. You've got this nitrogen to this nitrogen bonded here. Oops. I may end up turning that feature on the Apple Pencil off because it's very sensitive. It's a great feature, but I tend to double tap my pencil because I shift my pencil in my hand quite often. So anyway, and then you have this here. So I'm going to leave the other lone pairs off just for a second while I'm talking about this. If we look at just this part here, okay, just this part here, we know, so what I'm going to do is this. We know that if we had just this right here, there would be these electrons here, this lone pair pushes this way, and we have seen, like with water, with other molecules, that, and we've got a nitrogen attached here, right? What we've seen happen is they would push these down this way, and we would see something that looks sort of like this, right? That's what we would see. And so that half of the molecule is being affected that way. It is shaping that particular way, right? So let's leave that right there, all right? Let's leave that right there. Let's just keep this visualized right here. So now let's look at this other side right here where we have this nitrogen, right, to this oxygen, double bonded to this oxygen right here, right? And then we know over here it's going over here to this nitrogen, right? There is not a lone pair here. It is positive right there. If there's electrons not, if there's not as much electron density there, then it makes sense that the lone pairs that you see here and this double bond and everything right here, what is happening is there's a push this way, which means this would push out this way just a little bit, and this would push out this way just a little bit as well, right? So you would get something that looks like nitrogen, we've got an oxygen, there's our double bonded to that, and it's going up to this nitrogen, right? Now, so let's think about this for a second. If I bring this up here, and if I overlay this, you can see that overall, it looks like we're getting a shape that looks like this, right? Right? That's the magic of a digital sort of drawing board like this. You could see that I could literally bring the two pieces together. Now, if we go back in and oh my gosh, this Apple Pencil, I love it, but man, it is sensitive. If we complete, right? If we complete our octet, now we fill out everything back in with what we know is there, right? And then don't forget, we have those right there. We now have right here this right here. This is the best Lewis structure right here. This is the best structure because it takes into account our VSEPR structures. It takes into account the fact that three-dimensional modeling is occurring. I mean, things are bending according to the way they are being pushed and pulled. And when I say things are being bended, I mean the atoms are being bent and angled differently accordingly. So that would right here would be the best structure for the dinitrogen trioxide, right? And of course, we know that our double and triple bond, our double and single bond on that nitrogen is going to change. So of course, that's going to oscillate back and forth. But essentially, there you go. There is everything. It's spaced out really well. Follows all the octet rules. Satisfies the formal charge law as best as possible, where almost everything has the lowest possible charge, right? So remember, so now we know we can come over here, put our negative symbol, we put our positive symbol, and now we can turn this in for a grade, and we are good to go, and we can feel confident about this. All right, that was a long one, but that had a lot of good detail that brings in a little bit of everything, and really helps give perspective to that. You have to be able to build a Lewis structure. You've got to be able to count the formal charge properly, and then going from there, apply any sort of VSEPR interactions that are occurring. All right. go work on those practice problems and check your work. Reach out to me if you need any assistance, and I'll be more than happy to help. It's always great learning with you. Hope to hear from you soon. Hope to learn with you soon, and take care. Go get some coffee. Y'all have a good night. Bye.